Good morning. This is video number 3. I don't know if it's morning for you, but it's morning for me. I thought this joke was appropriate, and that's how much I love you guys. Love has no limit. Okay, so our targets are to find both infinite limits and limits at infinity, horizontal and vertical asymptotes, and we're going to use a dividing strategy to find a limit of a rational function. Okay, so let's start by just sketching the graph of 1 over x, and you may remember what it looks like. Whoa, that's pretty fat. Let me fix that real quick. And that's crooked, but there we go, like that. Remember that graph of that rational function? So in algebra, we would talk about end behavior. So as x approaches infinity, y is actually approaching 0. And as x is approaching negative infinity, y is also approaching 0. But now that we're in calculus, we can describe end behavior as limits. So let's write this end behavior in limit notation. So we're going to do the limit as x approaches infinity of 1 over x is equal to 0. So these two basically mean the same thing. And we can write the limit as x approaches negative infinity of 1 over x is equal to, and if as x is approaching negative infinity, that's going to equal 0. Okay, and we have two asymptotes here. We have an asymptote of the x-axis, and the y-axis, so we can list those as x is equal to 0. That's the vertical asymptote. And y is equal to 0 is our horizontal asymptote. Okay, so let's take a look at what the limit could be here at positive infinity and negative infinity. So the first thing we're going to do is sketch the graph of that, and I'm not quite sure what it looks like. So let's get to our calculator here. Whoops, it's over here. And I'm going to make a fraction bar. And instead of t's, I'm just going to use x. And my square root button is right here on the Inspire. X squared plus 1, I think. Okay, so here's this function right here. And now that I think about it, it kind of makes sense, doesn't it? So what does the limit look like as x approaches infinity? It looks like it's getting really, really close to 1. And as x is approaching negative infinity, looks like it's approaching 1. You could always verify with a table to see as well. Put in a really large value and see what you get. But for time, we're just going to go ahead and realize that the limit on the right-hand side at positive infinity is 1, and negative infinity is negative 1. So let's sketch the graph. So we'll label these. Oops, that's negative 1 and 1. And it kind of goes like this. Almost looks like a cubic function, doesn't it? Whoops, doesn't it? Okay, so let's write the end behavior. So we have the limit as x approaches infinity. And I'm going to be kind of take a shortcut and just write r of t. You always have to have a function after your limit. You can't just write the limit. You have to say the limit of what? So at positive infinity, that's equal to 1. And the limit as x approaches negative infinity of r of t is equal to negative 1. So we have a horizontal asymptote at y equals 1 and y equals negative 1. Okay? All right. So let's talk about horizontal asymptotes and end behavior. And with rational functions, you can pretty much just look at the function and figure out what the asymptote is. So if a rational function is top heavy, and let me show you what I mean by that. Let's say that f of x is equal to we'll do an x cubed minus 2x squared plus 1 over, we'll do x squared. And by top heavy, I mean you look for the leading term, the term with the highest exponent. So the highest exponent is in the numerator. So this numerator at infinity is growing much faster than the denominator. And so just imagine that. Anything to the third power is going to grow so much faster than something to the second power. So in this case, the numerator grows faster. And when that's the case, your limit is going to be either positive infinity or negative infinity. So let's just start with taking a look at positive infinity. So as x goes to infinity, and again, remember you have to put the function, I'm just going to write f of x, as this is going to infinity, this numerator is growing so much faster than the denominator, it's going to go to positive infinity. Now what about the other direction? Let's think about the limit as x approaches negative infinity. So now we know the numerator is growing so much faster, but we need to consider if it's going to positive infinity or negative infinity. So a negative number cubed is going to be negative. So we're going to have a negative number divided by, and a negative number squared is positive. So we're going to get a really big negative number because a negative divided by a positive is a negative. So the limit at negative infinity of f of x in this case is equal to negative infinity. Now, a limit equaling infinity or limit equaling negative infinity really does not exist. So these limits do not exist because a limit is a numeric value, it's a number, and infinity is not a numeric number, it's an idea. So in this case, the limits do not exist. Okay, how about a bottom heavy function? Let's do g of x is equal to 1 over x squared plus 4. Now in this case, the degree of the denominator is 2, and the degree of the numerator is really, it's like x to the 0. There's no variable here. So this is always going to be 1, and at infinity, this is just growing without bound. So think how big this denominator is. So 1 divided by a really, really big number is practically 0. 1 divided by 1,000,000, it's approximately 0, very close to 0. So the limit as x approaches infinity of g of x is equal to 0. That's because this denominator grows without bound and this remains a 1. Okay, this would also be true if you had, let's just do another one off to the side. Let's say we had x over x squared plus 2. This one is also bottom heavy. That denominator is growing so much faster than the numerator. The denominator will outpace the numerator, and therefore this will eventually go to 0 because this is growing so much faster. Okay, let's try the limit. I'm going to try to save some room. As x approaches negative infinity. And this is growing faster, even on the left-hand side. A negative huge number in the denominator is still going to go to 0. Okay, and 0 doesn't have a sign, so we wouldn't do a plus 0 and a minus 0, it would just be 0. Okay, so that's when the denominator is growing faster than the numerator. And then equal proportions is going to be when, I already used h, so let me try, let me do r of x. Let's say r of x is equal to 2x minus 4 over 4x plus 1. Now in this case, the variables are growing at the exact same rate. And what we're going to want to do is, I'm just going to get a different color to highlight, is you want to circle or pay attention to the leading terms. So these terms are going to determine what's going on with our function. So when you have equal proportions, meaning your variables, your leading term has the same degree. So this is the first degree and the first degree. The limit is simply going to be the coefficients. So the limit as x approaches infinity, that's a weird m, of r of x is going to equal 2/4, which is 1/2. Okay, and our limit as x is approaching negative infinity, if we take a look at this, we have a negative number divided by a negative number is going to be a positive number. So we're going to continue to look at our coefficients, and that's also going to be 1/2. Okay? All right. Next, let's take a look at the squeeze theorem. The squeeze theorem is also going to apply at infinity. So the first thing we're going to do is decide on a function to compare this to. And so what I'm going to use is -1/x. Oh, my pen's getting slow. And 1/x, and I'm going to see if maybe those two squeeze this function in between them. So let's go to our calculator, and we're going to put all three functions in. I'm going to make a new page. Okay, so let's do 1/x to start. And then I'm going to graph -1/x. So to make a new function on the Inspire, you just do tab. And then I'm going to do control fraction bar, -1/x. I'm doing something weird. I'm not quite sure what I'm doing to make that syntax error, but okay. Okay, there's -1/x, so there's our boundaries. So now let's try entering sine x over x. 1/x is going to 0, -1/x is going to 0, and because this function occurs in between, this is also going to 0. Okay, so let's go back to our notes. And let's draw a picture. So we have verified that sine x over x is in between these two functions, and the limit at infinity is equal to 0, and the limit at negative infinity is equal to 0. So therefore, we know that the limit as x approaches infinity of sine x over x is equal to 0, and the limit as x approaches negative infinity of sine x over x is also equal to 0. Okay, and that's what we've got for today, and to the next time, our next video, we will keep working in section 2.2. Okay, thanks and have a great day.